Oh, that would be. Try that next time.
My thought was, I say that when you go to and that we can cancel. If you do that, then you'll probably. Yeah. Yeah, like I was supposed to have my death yet. So some of the. Yeah. But like, yeah. I did not. It's like.
I'm gonna do these better questions, so, I mean, the worst, like, I think so.
Yeah.
The most I face this the whole thing.
It's true. But it's like.
I think that's probably what it wants.
Everyone knows.
Are you talking about?
Talking about.
First question, you were starting.
Yeah, first question when it talks about,
That being a lot larger than R.
yeah,
Oh.
it's like you could either have it go to 0, or you could come up with a, like you do the first Taylor expansion of it and then put that in. Like there's often there's that one. And I think it is that second one because when it's like one is a lot larger than the other, they almost always do the first Taylor expansion rather than. Just unless, but it's a limit, it's that, so it's
That's what I did.
I took the limit at first and then I thought.
I did too, but then it's kind of like there's a better way.
The first question when it's asking about like what said much larger than 2.6.
Yeah.
Yeah.
So yeah,
And it's the first, I'm pretty sure it'll want a first like Taylor extension rather than just like a limit where it's 0.
What did they do in the textbook? An example, just like that.
I'm not even sure.
Component and they called it out, it's like, I'm not, it's simply. I don't know what I'm
Really?
Oh, maybe.
So many fields. Where does the limit?
Right.
Oh, so there's one, it asks for the limit, and then the next one asks about that much larger than like or whatever. And I'm from all my other classes, when it says like one thing much larger than the other, it asks for like the first Taylor extension, not just like the limit.
In the textbook, they just did a hand wavy thing and we're like, this is what it turns into if we take that much bigger than L. And this is what it turns to if we take L approaching.
Oh, you're saying, yeah, but it says also check the case for Z being much bigger.
That's on the
Yeah,
same
yeah,
page.
that case. You could do one where you would have it, then it goes to 0.
All right.
Another where it goes like.
Let's get started. So we were talking about the
infinite square well, and we were going to try to solve the time-independent Schrodinger equation for this square well. So I know that you've seen this in Physics 200, but I believe we'll do this in quite a bit more detail than you did in 200, and we'll see some additional insights, I hope. So let's just remember the time-independent Schrodinger equation. So there it is. These lowercase psi's are the so-called stationary states. They're states of definite energy. They, when you act on them with the Hamiltonian, which is just the left-hand side of the time-independent Schrodinger equation, you get the E back again. Okay, so what we're going to try to do is, first of all, we're going to solve for the stationary states in the infinite square well, and then we're going to try to reconstruct the full time-dependent wave function, which is a solution to the time-dependent Schrodinger equation, using this sum, where we'll have to find the values of these coefficients Cn. Okay, and so we had this in our notes last time, infinite square well. The potential is defined to be 0 between the limits minus a by 2 and plus a by 2, and then it goes to infinity outside that range. Griffiths does this problem. It's just the whole x-axis is shifted. So his goes from a equals 0 to, x equals 0 to x equals a. Otherwise, it's the same. What we already decided is that outside the well, where the potential goes to infinity, the wave function has to go to 0. The little psi must be equal to 0. So what we're left trying to do is to try to solve the time-independent Schrodinger equation inside the square well. Okay, so let's see what happens. So inside the well, V is equal to 0, and the time-independent Schrodinger equation becomes, well, all we're going to do is take this expression here and put in V equals 0. So we just have these two position derivatives acting on psi is going to be equal to E times psi. All right, so if we do that, the coefficients out front were h bar squared over 2m. And then we had two derivatives with respect to position. Has to be some constant E. It's going to be the energy times psi. Okay, and this is valid for the absolute value of x between plus minus a by 2. Or I guess I should say the absolute value of x should be less than a by 2. All right, so I'm just going to collect these constants together, and let's write it in the following way. Oops, this is going to be a position derivative. It's minus k squared over psi, where k is going to be E times 2m divided by h bar squared. So k is equal to 2m times E divided by h bar. If I take the square root, we'll put the square root in there, and the h bar squared becomes just h bar. All right. You might recognize this. This looks a lot like two derivatives of x with respect to, say, time is minus some omega naught squared times x. That's like the simple harmonic motion kind of expression. But anyways, what we need is a function where we take two derivatives and we get a minus sign times the function back again. What kind of functions do that? I take two derivatives of this function and I get minus the function back. Great. Yeah, sine and cos do it. Griffiths uses sine and cos, okay? What I'm gonna do is I'm gonna be contrarian and I'm gonna use a different function. I'm gonna use the exponential. The exponential, if I take two derivatives of it, I just get the exponential back, but if I have an I in the argument, then I'll get an I squared coming down. That will give me my minus sign. So the reason that I'm doing this different than Griffiths is just to show you that you can approach this in different ways and come out with the same solutions. Okay, so let's first of all, let's just verify that this is actually a solution. We can take one derivative with respect to x, we'll get an ik a e to the ik x, and then we'll get a minus ik b e to the minus ik x. And then if I take a second derivative, I'm going to get another ik coming down, so I'll get I squared k squared, that's minus k squared. Same thing here, take another derivative, the minus signs cancel, but I get an I squared, the minus sign comes back, so we get a minus k squared e to the minus ikx. So I can take out that common factor of k squared, then I have a e to the ikx plus b e to the minus ikx, but that's just our original. Yes, that's the solution. And so indeed, that is a valid solution to this time-independent Schrodinger equation. Okay, so what we have is we have two unknown constants. Well, in fact, maybe even three. We have a k, which we've written in terms of this stuff, but really one of the things we're after is finding e, so we don't have e yet. And we have this a and b. So our task now is to find these constants, and the first thing we'll do is we'll try to apply the boundary conditions. Okay, so we need to enforce boundary conditions to determine. Let's start with a and b. Okay, so our boundary conditions is we said that the wave function has to go to 0 at plus minus a by 2. So psi at x equals plus minus a by 2 has to be 0. So let's start with x is equal to plus a by 2. All right, so at a by 2, we want that to be 0. And we're just going to sub in to our solution at the top of the screen here. I'm just going to put in where I see x, I'm just going to put a by 2. So we're going to get a e to the ik a by 2 plus b e to the minus ik a by 2. All right. Let's see. I want that to be equal to 0. So what I'm going to do is I'm going to multiply through by e to the ik a by 2. If I do that, I'm going to get a 0. 0 times whatever, 0. A e to the ik a. When I multiply by e to the ik a by 2, get rid of that 1/2. And I'm going to cancel this one, so I'll get a plus b. Okay, and so that tells me, therefore, that b is equal to minus a e to the ika. Okay, so what I'm going to do is I'm going to substitute this value of b back in to our wave function, our stationary state. So psi of x is going to be a e to the ik. It was x. And then we'll have b, but for b, I'm going to write minus a e to the ika times e to the minus ik x. All right, there's a common factor a, so I'm going to factor that out. But at the same time, I'm going to factor out this e to the ika by 2 that we just multiplied through. I'm going to factor that out again. So we'll put it e to the ika by 2. And I think we'll see why I'm going to do that in just a second. All right, so what happens when I do that? I'm going to get this e to the ikx. But I pulled out this factor. And so to compensate, I have to put it back in with the opposite sign. So that if I did multiply this through again, it would cancel here. We get the same thing. Okay. And then for the second term, we'll have a e to the minus ikx. And then I took out half of this. So we'll have to leave the other half behind. Okay. Now, that looks a little, sorry, I have a mistake.
Yeah, you lost.
I lost a negative sign. Indeed, I did. So let's fix that. All right, good. What I'm going to do now is I'm going to combine these exponentials. So we have, let's see, how would we write this? A e to the ika by 2. All right. So we'll do e to the ik x. So I'm going to pull out an ik. I'm going to get a minus a by 2. All right, and then over here, I'll get a minus e to the minus ik, and we'll have an x. And then we're going to get a minus a by 2. You can already see that this is kind of doing something we like. We've just shifted our x coordinate by half of a. And so that's sort of making our solution already equivalent to Griffith's because our potential is just shifted by a by 2. All right. How can I write this in a simpler way? I have e to the ix minus e to the minus ix. That's like a sine function, right? What we need is, let's see, I believe this is just 2j sine of x minus a by 2. Sorry, I forgot my k. I need my k in there. K x minus a by 2. All right, so therefore, what we have from our, after applying our first boundary condition is 2j a to the e ika by 2. Those are all the prefactors, and they are multiplying sine of kx minus a by 2. All right. So let's see if we can apply the next boundary condition. So the next one is x is equal to minus a by 2. So our other requirement is that psi at minus a by 2 has to be 0. And so I'm just going to go in here and put in a minus a by 2 wherever I see x. And I only see x in the argument of the trig function. So that's where it'll go. So I will have, let's see, 2j a e to the ika by 2 sine of k. And I'm going to put in minus a by 2, and I'm going to have another minus a by 2. It's just a minus a. Sine of minus x is minus sine x. So let me take the sign out of the trig function. And so therefore, what we find is 0 is equal to minus 2j a e to the I k a by 2 sine of kx. Ka, sorry. All right. So now we have the situation where we're trying to find some of these unknown constants. We need this thing to be equal to 0. One way to do that would be to just say a equals 0. But that's not interesting, because if I set a equal to 0, we just have no wave function. There's no particle in the box. So we don't want to do that. We can't set a equal to 0, because then psi is just going to be equal to 0, and there's no particle. I said box, I guess I should have said no particle in the well. All right. So all these other things are just constants. They're not going to be 0. So it must be that the sine Ka has to be 0. So therefore, we must have to satisfy sine Ka is equal to 0. And sine is equal to 0 whenever the argument is some integer multiple of pi. And so Ka must be equal to n pi, where n could be 0, plus minus 1, plus minus 2, and so on. This is exactly where we're going to see this quantization. And the quantization comes from the boundary conditions. Okay. So therefore, K is quantized due to the boundary conditions. But if you remember, K was defined in terms of the energy E. And so Kn is equal to n pi over A. I put a little subscript n just to remind us that this has many values. Remember, we said when we solve the time-independent Schrodinger equation, we're going to get a family of solutions. Well, here it is. We have an infinite number of solutions because we have an infinite number of values of n that we could enter. Okay, let's go back and look at K. Here it is, root 2me over h bar. So K was equal to root 2me. I made my root too big. 2me. I'll put a subscript n on our e as well, and then we divide by h bar. And so let's go ahead and solve for the energy. N is equal to, let's see, it's going to be h bar k, and then we have to square it. So we're going to get an h bar squared k squared. And then we're going to have to divide by 2m. This is kind of nice. The reason we used k in our notation is because h bar k is like momentum. So h bar k squared is momentum squared divided by 2m. That's like kinetic energy, right? Okay, and then we could, if we wanted to, we could put in n pi over a for kn. And so this is equivalent to h bar squared. How do I want to do this? Let's write it this way. Let's do n squared pi squared h bar squared over 2m a squared. So this quantization of K is really a quantization of the energy of the particle. So the energy of the particle in the well is quantized. Okay, this notation for K is also suggestive. K is usually used for wave number, 2 pi over lambda. And so we're going to expect K to be somehow related to the wavelength of these stationary states that we're solving for. Okay, so let's go back to, we still don't have A, but let's go back to our wave function. We now have quantized K. And so we are at the stage where psi of x is equal to, what did we have? Let's go look back at everything. 2ja, so 2ja, e to the I k, was it a by 2? Yeah. I'll put an n over here, a by 2. And then we had sine of kn x minus a by 2. I think that's what we have. I think that looks right. All right. We still don't know A. What would we do to find A? Normalization. That's exactly what we're going to do. Before I do that, if you go look up Griffith's solution, he doesn't have the minus a by 2. We already talked about that. That's because his potential is shifted relative to ours. But he doesn't have this kind of factor either, the e to the ik a by 2 in front. Now, in quantum mechanics, everything that we could measure is going to be related to the absolute square of our states. And when we do that absolute square of the states, this e to the I times some constants is always going to cancel. So this has no physical significance. Even if we were to calculate expectation values, it's going to be the integral of psi star times an operator times psi. And so you're still going to get these factors canceling. You can, as long as there's no x in here, like if your momentum operator has derivatives of x, so we can't have an x in here, but as long as these are constants, it's always going to cancel. And so, yeah, go ahead.
If it's a like linear combination of states like we were doing last time, then we wouldn't just be able to remove that. That's an important part that's required, right?
Yeah, we are going to do that. We're going to reconstruct the full thing and we'll see how that works out. So this is physically insignificant. So all calculated quantities depend on, sorry, I should say all measurable. That's a better way to say it. All measurable quantities depend on psi squared. Okay, so what I'm going to do is I'm going to define all of this as AK prime, some other constant, and we're going to use normalization to find it. So let's use normalization to find AK prime. So normalization requires that if I ask, what is the probability of finding my particle anywhere inside the well? That has to be 1. And for us, the domain of our well is minus a by 2 to plus a by 2. Okay, and so we require this to be equal to 1. Okay, so 1 is equal to, let's see, the integral from minus a by 2 to a by 2 of ak prime, and I'll put a star there. And then we have sine kn x minus a by 2. And then we have to multiply by, so that's the conjugate of the wave function. So now we multiply by just the regular wave function, ak prime, and then we get another factor of sine kn x minus a by 2. I'm gonna run out of my room for my dx. Okay, so we'll get the absolute value of ak prime squared, the integral from minus a by 2 to a by 2, and then we have a sine squared. So sine squared kn x minus a by 2 dx. All right. For me, the easiest way to do this is to change the sine squared using a trig identity. The trig identity I want to use is that sine squared x is 1/2 of 1 minus cos of 2x. Okay, so this is the same thing as 1/2 of 1 minus cos of 2 kn x minus a by 2. And so I'm going to make that replacement, and let's see what we get. We get ak prime squared divided by 2, integral from minus a by 2 to plus a by 2 of 1 minus cos 2 kn x minus a by 2. Like so. All right. So this is not so bad. We can do this integral. The 1 is going to integrate to an x. I need my dx. And the cos is going to bring out a factor of 1 over 2k. But then this is going to turn into a sine. And let's see what happens when we put in the limits here. So let's do the integral a k prime over 2 the ak squared. And then the integral gives us an x. It's a minus 1 over 2 kn sine of 2 kn x minus a by 2. And close my bracket. And minus a by 2 to plus a by 2. All right. So let's just mentally think about these limits. When I put in a by 2, I'm going to get sine of 0, and that's 0. When I put in minus a by 2, I'm going to get sine of 2kn at minus a. But k was n pi divided by a. So the a's are going to cancel. We're going to get a 2n pi. And it doesn't matter what I put in for n, as long as it's integer, sine of 2n pi is always 0. So this is going to be 0 at both limits. And what we end up with is, oh, come on, let's go. Therefore, 1 is equal to ak prime squared over 2. And then for the x, we get a over 2 minus a over 2. And so that just ends up being a. And we can solve for ak prime is equal to, let's see, it's going to be root 2 over a. Notice that this, we labeled our constant with a subscript k because we had this e to the ik in there. But when we go and do normalization, all that k dependence goes away. All right, so therefore our wave function has an overall normalization constant of a over 2 square root, and then we have sine k x minus a by 2 and k is n pi over a. Let's put my subscripts back in. All right, perfect. So those are the stationary states, and we found their energy already. Let's just think about the values that we should consider for n. We could put in n equals 0. But when we put in n equals 0, k equals 0, and the sign of 0 is 0. So again, the wave function just vanishes. There is no wave function for n equals 0. So the k n, well, okay, n equals 0 is not interesting because then phi is equal to 0. Okay, no particle in the well. No particle. Let's think about the negative values of n. So n equals -1, -2, -3, and so on. And so these just correspond to well, if I put in a negative n, my k becomes negative, but that's inside the sign. The sign's an odd function. So the negative sign I can pull out, and I would just get minus this wave function. So this is just the same thing as minus phi n of x. However, all measurable quantities, like we already argued, are going to be determined from the absolute square of these stationary states. And so the negative sign doesn't matter. It doesn't give any new information that's not already in the positive version of n. So, however, all measurable quantities come from the absolute square. So the negative n values do not give any new information. All right, and so that means over here, we just have to worry about n equals 1, 2, 3, all the positive integers, not n equals 0. Okay, so let's draw some of these solutions. We know what the sine function looks like. So let me draw the potential. Here's x. Here's, let me use these dots properly. So here's the center, and I'm going to plot v of x here. And I'll go 1, 2, 3, 4 maybe. Here's a by 2. This goes to infinity. That's all infinite. And 1, 2, 3, 4, right around here is minus a by 2. This is infinite. Okay, so let's see, where's our wave function? There it is. So we could draw some of these states. Let's put in n equals 1. Then k is pi over a. So k, so okay, let's do this. So n equals 1, k 1 is equal to 2 pi over lambda if it's a wave number, and that's also equal to pi over a. So if I solve for this, lambda is equal to, let's see, a by 2, does that make sense? Cancel the pi. Lambda is equal to 2a. Let's get that right. All right, so the wavelength is twice the width of the well, or half a wavelength fits in. we know that the wave function has to go to 0 at the boundaries. And so the only way we could fit half a wavelength in there is like so. So this is the n equals 1 solution. If we did n equals 2, we would find that lambda is equal to a. So 1 full wavelength fits inside, and we would get something like this. Draw this right. This is n equals 2. And, you know, you can probably see the pattern already. We're going to get 3a by 2 when we put in n equals 3. And so every time we increment n, we add half a wavelength into our solution. Or if you'd like, we add a 0 in the wave function. I'm offsetting these vertically just so that I don't have to draw them on top of each other. So let's see if I can get this right. So it's going to be something like that. This is the n equals 3 case. And then you can keep going. Okay. So those are the solutions. Let's look at some of the properties of these solutions. So let's note that the stationary states by n of x, these are our separable solutions, are orthogonal. I alluded to this, I think, in the last class. Well, in fact, I'm not going to prove it. I'm going to show you how you can prove it. So that is the inner product. So inner product is just a fancy term for this integral where you take one of the stationary states, say the mth state, and we'll take its conjugate, and then we'll multiply it by the nth stationary state, and we'll integrate over our domain. Now for us, these are just sine functions. And you may remember in Physics 232 that when we were talking about the Fourier series, we showed that if you integrate two sine functions of different frequencies over some periodic interval, that integral vanishes unless the two frequencies are equal to one another. And so this is going to be 0 when m is not equal to n. And if the two frequencies are equal, it'll be equal to 1. Now, in fact, we sort of did that integral already, right? So I think when we did the normalization, we did this integral, we showed that the cos vanished, and we had just this one left over with the 1/2, but then we picked up double the length there. So we kind of did that part of it. Okay, so the proof for psi n of x is equal to root a 2 over a sine of kn x minus a by 2 is left as an exercise for the student. We did this proof in Phys 232. In fact, part of that proof was probably one of your assignments when discussing Fourier series. All right. So let me just introduce some notation. And you probably have seen this already. So let's recall the Kronecker delta. Kronecker delta. So delta mn, and it was defined in the following way. So it's equal to 0 when the indices m and n are not equal, and it's equal to 1 when the indices match. So this is very convenient because it allows us to write our orthogonality condition the following way. Then we can write that psi m star psi n star integrated over our domain. In fact, I'm going to leave the limits of the integration out for now, is equal to the Kronecker delta. And although we've done this, we've demonstrated this for a specific case of the infinite square well, this turns out to always be true, and we're going to do a general proof in the next chapter. Okay, and so what we would say is the size are orthonormal. So that means they are orthogonal to one another, and they are normalized. Okay, so the other property that our stationary states have, our solutions to the time-independent Schrodinger equation, are that they form what's called a complete set. And we're not going to prove that. If you read Griffiths, he says that the proof is long and arduous, and he's a theorist. I'm going to take his word for it, that it's a lot of effort. So we're not going to prove it, but it is a general fact that what I could do is I could take my infinite set of stationary states, and I could write any other function inside this domain as a linear combination of those states. It's exactly analogous to the Fourier series. The Fourier series is a bunch of sines at different frequencies. I could add them up with different coefficients in front of each term. As I adjust those coefficients, I can make any other periodic function. Okay, so the stationary states are also a complete set of what are going to be known as basis functions. That is, any other function on the domain. So in our example, our domain is minus a by 2 to a by 2. In our case, can be expressed in terms of psi n. Okay, so explicitly what that looks like is I could take any function f of x, and I could write it as n equals, not n equals 0, n equals 1 to infinity of Cn psi n of x. So the only job is to find the correct coefficient so that when you evaluate the sum, it does match your f of x. So for our specific example of the infinite square well, we had our normalization coefficient, our constant for psi, and then we have the sum of n equals 1 to infinity of Cn, which we don't know yet, And then for us, we had sine kn x minus a by 2, like so. I'm going to call this equation 2. I think we have an equation 1 up there, don't I? Yes, I do. Equation 1 is our orthonormal condition. All right. What I want to show you is that it's actually not so difficult to find these CN coefficients. We're going to actually use our orthogonality, equation 1, to find the CNs. So we can find CN coefficients using equation 1. Okay, so to see how, let's consider the following. I'm going to take one of our stationary states, one of our solutions to the time-independent Schrodinger equation, and I'm going to multiply it by f of x and integrate. Okay, so for f of x, I'm just going to put in the sum. Okay, so that's going to be, let's see, the sum n equals 1 to infinity. And then what do we have? We have the integral. Psi star. And then we have to multiply by the f of x. We already have the sum. There's a Cn. Okay, the Cn's a constant. I can pull it outside the integral. We'll put it right there. And then all that's left is the psi n. Okay, psi n star dx. But this integral is exactly this integral, and it's equal to the delta function. So this is exactly delta mn from 1. All right, so what do we have left? This is n equals 1 to infinity Cn delta mn. Now, I don't know, for those of you that took 232, we called the delta function the killer of sums. And here, it's back to work again, okay? Because if I actually write out some of these terms, what am I going to get? I'm going to get C1 delta M1 plus C2 delta M2 plus and so on. There's going to be a special one. There's going to be the n equals m case. And plus more. And for every one of these deltas, we're going to get a 0 except for this one. This is 0, this is 0, but this one is 1. And so in the end, all we get is Cm. So we can get our nth coefficient by evaluating this integral. The psi m star times f of x integrated over our domain pulls out the coefficient Cm. We're going to do an example where we'll see this in practice. So in general, the Cn coefficients are obtained from, okay, so Cn is equal to, I'm going to change the m subscript to an n, but it's just psi n star times f of x dx, and I'll call that equation 3. So the reason we're doing this in sort of slow detail is because all these properties that we're working out, equations 1, 2, and 3 are general properties that we'll always have. They're not just valid for the time, for the infinite square well. So although 1, 2, and 3 have been demonstrated for the infinite square well, they hold, these properties hold generally. We will prove the orthonormal part, the delta function part, in chapter 3, but completeness, like I said, are going to go without proof. All right. So the stationary states that we've just solved, these psi n of x's, these are the sine functions that fit inside of our square well. They are an infinite set of solutions to the time independent Schrodinger equation. Each of these states evolves in time according to. Okay, so remember when we did our separation of variables solution to the time dependent Schrodinger equation, we had an equation for phi which we could solve. And what we said is that the way we put the time dependence back in is we take our stationary states, which contain the x dependence, and then we multiply by e to the minus I e n t over h bar. I wanted to put an n in here because now we have an infinite set of these. Okay, we know this. We just calculated that. We also found the energy. So we know all of these things. So we now have these solutions. Okay, so En we get from our boundary conditions. All right. Internet connection unstable. All right. So what we would need to do to get the most general solution to the full original time-dependent Schrodinger equation, which was the axiom of our quantum mechanics, is we need to just take superposition of all of these. Okay, and so the general solution to the full time-dependent Schrodinger equation is phi x of t is the sum over all infinite number of the solutions, the stationary states, like so. Okay, and so we could write this down for our infinite square well, and it's going to look like this. Equals n equals 1 to infinity Cn 2 over pi square root was our normalization. Then we have the sine kn. Kn was n pi over a, x minus a over 2 for us. And then we had the exponential, contains the time dependence. It was minus I en. For us, en was n squared pi squared h bar over 2ma squared. And then we need our factor of time. And that is the full solution to the time-dependent Schrodinger equation for the infinite square whale potential. And we have a prescription for finding the CNs. All right. So to see how this all works, let's imagine the following. Suppose you're given a solution to the time-dependent Schrodinger equation at t = 0. Okay, so if we put in t = 0, what are we going to get? Well, t = 0, this exponential is just going to go away, and it's just the sum of Cn times the stationary states. Okay, so that's just n = 1 to infinity, Cn times psi n. So this is equation 4 with t = 0. Okay. So let's find the CNs. We would take psi m star times psi x at time t = 0. This is now like our f of x that we did before. Okay. So this is our f of x. It's right here. We just put them in, and it's equal to the sum of n = 1 to infinity. There's our coefficients, and then there's our integral, psi m star, psi n dx. But this, we already know, is delta and m. And then we know that the sum of c times the delta function is just going to select that one value, Cm. And so all of this is just Cm. All right. And so we could write down again, instead of f of x, the coefficient for our full wave function at time t = 0 is given by this expression. So what we can do is, given some initial wave function, we can work out these coefficients, and then we could substitute them back into equation 4 with CNs known, and we already have the time dependence. We could watch the time evolution of our wave function. So given an initial wave function psi at x and t = 0, we can use the stationary states psi n of x, little psi, from the time independent Schrodinger equation to calculate all Cn values. We can then sub into 4 to get the wave function at all future times. At future times. Okay, good. So that's sort of a summary of the mechanics. How much time do we have? We have 15 minutes. So let's do an actual example where we'll go through this process and actually find, I'm going to give an initial wave function, and we're going to find the coefficients. Okay, so example. Suppose psi x of 0. This just has to be given. Okay, it doesn't come from anywhere. I made it up. The only thing that I have to be careful about is that this has to satisfy our boundary conditions. That wave function has to go to 0 at x equals plus minus a by 2. So what I'm going to do is I'm going to say this is going to be 0 from a by 2 to a by 4 on the negative side and on the positive side. This would have to be an a by 4 here. And then I'm going to make it root 2 over a from, oh crap, I forgot my minus, this would be a minus sign. So from minus a by 4 to 0. And then it'll be minus root 2 over a from 0 to a by 4. I picked these values just so that the wave function is normalized. Okay, so it's normalized and it has the right boundary conditions, so it's a valid starting point. Okay, and so the question is, find phi x of t. Okay, so what we'll do is we'll first determine, why don't we plot this thing first? So phi x at 0, x. And so I'll put in minus a by 2 here, minus a by 4. This is 0, a by 4. And this is a by 2. Okay, so it's going to be 0 here and here. And then it's going to be a positive constant here. And it'll be a negative constant here. So that's our initial wave function. Okay, so let's find the Cn coefficients. Okay, so we said Cn is going to be psi n star of x times our initial wave function. And we're going to have to integrate from minus a by 2 to a by 2. Okay, but our initial wave function is just piecewise smooth, so we have to break this integral up into parts. In fact, we don't care about minus a by 2 to minus a by 4 and a by 4 to a by 2 because there the wave function was 0. So what we have to do is we have to say this is going to be, so let's look, where's our wave function? Where's little psi? Sorry, we'll find it. There it is. So there's the coefficient, and then it's just a sine function, k times x minus a by 2. That's all we're going to put in. Okay. So let's see, we're going to get our normalization constant. That, and then we're going to have to separate this integral into pieces. We're going to have a piece that's going to go from minus a by 4 to 0. Then we'll put in our wave function, and we're going to pick up another one of these factors because that's what phi of x0 is equal to. So phi of x0 is going to be root 2 over a. And then we have our sign, kn x minus a by 2 dx. And then we have plus, we have another piece. In fact, it's going to be a minus. We'll go from a by 4, 0 to a by 4, probably. 0 to a by 4. This 2 over a is from our initial wave function. The minus sign is from that initial wave function right there, minus 2 over a square root. Okay, and then we have the sign again, kn x minus a by 2 dx, and then close bracket. All right. So these are our CNs. These intervals aren't so difficult to evaluate. Let's see what we get. All right. There's this common factor I can pull out. It multiplies that factor out front, which is the same. And so we just get a 2 over a, an overall constant. And now let's integrate. So we're going to pick up a minus 1 over, so we integrate sine, we get minus, I think, don't we? I think we get a minus 1 over kn, and we get a cos knx minus a by 2. And then the limits of integration are minus a by 4 to 0. Okay. And then we're going to do the same integral again. We pick up a minus sign, but we already have a minus sign out front, so we end up with a plus. So we get a plus 1 over kn cos. Let's see, kn x minus a by 2. And we're going to go from this time 0 to a by 4. So. All right. So there's a common factor of kn we can pull out. Kn was n pi over a, so 1 over kn is a over n pi. So we get a 2 over a over n pi. All right. Now let's put in some limits. We put in the 0 limit, we get cos of kn a by 2. Okay, so cos, if you put in the k value, it's n pi over a, and then we have an a by 2, the a's cancel, we get a 1/2. The minus sign doesn't matter, cos is an even function. All right, but sorry, this minus sign doesn't matter, this one does, so I'm going to put that minus there. Okay, and then if you do the other limit, you'll get a plus cos 3n pi over 2. If you do this one, when you do the 0 limit, you're going to get another cos of n pi over 2. It's also going to have a minus sign. And then if you do the a over 4 limit, this is a over 4 minus a over 2. That's going to be minus a over 4. This minus sign doesn't matter. So we'll get a cos with a divide by 4, n pi over 4. Okay, so that's it. We're just going to try to clean it up a little bit. So therefore, Cn is equal to 2 n pi. You get a minus 2 cos n pi over 2 plus cos 3n pi over 4 plus cos n pi over 4. If you actually work this out, what you'll find is Cn is equal to 0 when n is odd. If I put an odd number here, I'm going to get some cos of a multiple of pi over 2. So like 3 pi over 2, 1 pi over 2, 5 pi over 2, that's going to be 0. Same thing here. I'm going to get some, let's see, these will cancel when n is odd. Okay, I'll let you confirm that you can also write the following. We make a table of these values. So there's no odd ones, those all vanish. 8, 10, 12, 14. I'll write out a few of them. So this is 2 over pi, This one comes out to be minus 2 over pi. This is 2 over 3 pi. 8 comes out to be 0. 16 will be 0. 24 will be 0. 32 will be 0. All n's that are a multiple of 8. This is 2 over 5 pi. This is minus 2 over 3 pi. This one comes out to be 2 over 7 pi. And then you can just keep on going. So we just got all these coefficients. All right. So with those coefficients, we could sub into equation 4. And we could get psi of xt is going to be equal to n equals 1 to infinity. Cn, we now have the Cn coefficients. We solved for our stationary states. This is what they look like. We solved for the energy, which gives us the time dependence. This is what it looked like. Pi squared h bar t over 2ma squared. All right. So in the last 5 minutes, I want to show you what this looks like. I plotted this. Actually, what I did is I plotted the absolute square of this. Okay, and what the absolute square of this wave function tells us is the probability density for where we're going to find our particle inside the square well. And so let me show you what that looks like.
How many like degrees you can go up to?
I'm going to show you right now. So let's share the screen like so. All right, so I'll get rid of this. All right, so can I move this thing out of the way? A little sort of. All right, so I put a link to where I solved this on the course website. So if you click on that link, it should take you to a Jupyter notebook that you could launch. And so you're right, it's an infinite sum. I can't keep an infinite number of terms, but those Cn coefficients, they have the property that they get smaller and smaller and smaller as you go to higher and higher n, just like the series expansion of sine and cos and all that stuff. So what I did is I kept terms up to n equals 1,000. And I calculated the square of the wave function for 800 points between minus a by 2 and plus a by 2. So I won't bother trying to show you all the code. This takes about 45 seconds to run, and it's going to make a little video that we can watch. The reason it takes so long to run is because it has to calculate the wave function at 800 points of x for a whole bunch of different times, and then we'll watch the time evolution of this probability density. So hopefully this is running. Let's see. It is running. There's a little star there. We'll wait for that star to go away.
You can also make something like this in Desmos as well.
Yeah, you could make something like this in a whole bunch of different platforms. Okay, it's done. So let's go look at the output at the bottom. So here it made a little video for us. This is t equals 0. This is our wave function was 0 at the outer edges, and then non-zero in the middle. The reason it looks positive is because we're looking at the square of the wave function. And I'm just going to play this. And this is showing you the time evolution of this quantum wave function. And what we should think about is that this is telling us the probability if we were to measure, say, the energy of the particle in our square well, this is telling us the probability that we'll find it in a particular state. And so we're most likely to find our particle located out here on the edges at this time, but I can scroll through this frame by frame. Oh, and it happens to be one where it suddenly changes abruptly. And these are all the different wave functions at different times. There's one in here. Yeah, there's one moment where basically a uniform probability of finding it anywhere in the well, except it goes to 0 right at the center here. Okay, and so in general, this process that we followed in order to do this calculation applies to all of the systems that we are going to investigate. Most of the work is in finding the stationary states, solving the time-independent Schrodinger equation. After that, all the machinery is the same. We can expand functions in terms of these basis states, these stationary states, and then we can calculate the time evolution by having known these coefficients Cn and knowing the energy that gives us the time dependence, and we can construct this for any potential that we're given. All right, so that's it. Thank you very much. Have a good evening.